In this video, I'm going to talk about two applications. The first application I'm going to talk about is the break-even point application, and that's when you're solving a revenue cost problem. Let's define some terms. Revenue is the amount of money one takes in when selling products. So if X represents the number of products sold and P represents the price, then the formula for revenue is simply revenue equals X times P. Now the price could be a constant like $45 per item, and sometimes the price can be dependent on the number of items sold. Like for instance, you might have a price written as a function like 45 minus 0.01x. But since we're focusing on a linear function, we'll just keep our price constant. Now cost is the cost for a business to manufacture goods based on the number of X manufactured. And cost usually has two parts. You have a fixed cost. This cost is regardless of the number of items manufactured. Basically, it's your operating costs. And so fixed cost is generally a constant, like maybe $30,000 is the fixed cost for, say, a week of manufacturing. The variable cost is the cost based on the number of items X that are manufactured. For example, if it costs $25 to manufacture an item, that should say and, not and, an item, then the variable cost would be 25 times X. So the cost function actually is the fixed cost plus the variable cost. So for example, if I use the 30,000 for the fixed cost and the 25x for the variable cost, the cost function would equal 30,000 plus 25x. Now the break-even point is just the point at which the revenue and cost are equal. So let's look at an example of finding the break-even point. Suppose a company sells calculators for a price of $45 each. The weekly cost for the company is given to be $30,000 plus $25 per calculator. Find the break-even point. Well, we know the revenue function is 45x, and we know the cost function is 30,000 plus 25x. So to find the break-even point, you actually want to solve the equation revenue equals cost. And so what we're going to do is we're going to use a substitution. So if you think of this equation, revenue equals cost, let's substitute our revenue value in terms of x, 45x, on the left. And then on the right of this equation, we'll substitute our 30,000 plus 25x for cost. And then that will give me a linear equation. And I can easily solve this linear equation for x. So now all I have to do is subtract 25x from both sides, and I'll get 20x equals 30,000. Then just divide both sides by 20, and I get x equals 1,500. So we must manufacture 1,500 calculators per week to cover our cost. So that's the x value of a break-even point. And so if we manufacture less than 1,500, we'll experience a loss, and if we manufacture more, we experience a profit. If you want to know the dollar value at the break-even point, then plug in the x value. So I have no idea where 2,000 came from, but the x value is 1,500. So plug in the 1,500 into either the revenue or cost function. So it's easier to plug it into this revenue function up here. So I'm going to plug it into the revenue function. So I'll just have 45 times 1,500, and that will give me a total revenue of $67,500. And by the way, that would also be the value of cost. So if you plug 1,500 in up here for cost, you get the same thing. So the break-even point is 1,500 calculators for a revenue of $67,500. Now, if you were to graph these, basically what you would find is you would find that this would be the blue line here would be the revenue function, and the red line would actually be the cost function. And notice that if you look to the left of 1,500, remember this is 1,500, so if you look to the left of 1,500, your revenue would be below the cost function. So over here you would be experiencing a loss. But once you get beyond 1,500, your revenue is above the cost function. So therefore over here you're experiencing a profit. And so that's your profit. So And then, of course, this point right here where they intersect is your break-even point. Okay, now the other application I wanted to talk about was to solve for the equilibrium point. And the equilibrium point is basically where supply meets demand. So demand is the quantity of a product that consumers are willing to purchase during a time period. And that demand depends on its price. The higher the price, the lower the demand. And then lowering the price increases the demand. So if you think about like when the latest new iPhone comes out, it might be $500, and so in the beginning maybe only the people that have lots of money are going to buy it. But after the price drops to say $200, then the demand would increase. Okay. Now the supply, that the quantity of a product that a supplier is willing to sell during a time period also depends on the price. The higher the price, the more will be offered by the supplier. So going back to my iPhone example, when the iPhone is priced at $500, the supplier probably wants to supply as many as they can so that they can make a lot of profit. But once the price is lower, then the supplier is not willing to supply as many. Now, these equations actually use either X or Q to represent quantity, and they use P to represent price. So the quantity is the domain portion, and the price is the range portion of the function. And this can be confusing to explain because when we talk about increasing or decreasing price, we are actually referring to the y-axis. So it's a little complicated to talk about. Let me just go ahead and show you a graph here. Okay, so this blue line is the demand. So you can see that when the price is way up high, the demand is low, but when the price drops to a low value, the demand is high. And then you can also see that when the price is low, the supplier is not willing to supply many, but as the price increases, the supplier is willing to supply more. So these two graphs go in different directions. Okay, so let's say that you are given a supply equation and the demand equation for a particular item. And this example is the number of thousands of boxes of tea. So the quantity represents the number of thousands of boxes. So basically what you have to do is you set supply equal to demand. So you just set supply equal to demand, and then you substitute for supply this portion, and you substitute for demand this portion, and then that will give you an equation that looks like this. And then you just solve this equation for the quantity. So if I add 0.2q to both sides, I'll get 0.07q plus 0.2q. And then if I subtract 0.76 from both sides, over here I'll get 4 minus 0.76. And so then when you add 0.07q to 0.2q, you get 0.27q. And then 4 minus 0.76 is 3.24. And then divide by q, and you get q equals 12. So 12 represents 12,000 boxes of tea. So basically, if we supply 12,000 boxes of tea, then the consumer will theoretically consume that amount of boxes of tea. Now, we need to set the price, though, for that particular number. So to get the price, we just grab either one of these functions will work, and we plug in for Q, let's plug in 12. So if you plug 12 in here, you get 0.07 times 12 plus 0.76. And that equals 1.6, which represents $1.60. So the equilibrium point would be, the quantity would be 12, and the price would be $1.60. And that corresponds to where the two equations intersect graphically at the quantity Q and the price 1.6. And remember, the quantity is the x-axis, and the price is the y-axis. Okay, now in that example, I didn't have you derive the equation, but you can derive the equations if you've got enough information, and we assume that they're going to be linear equations. So here, let's suppose when an item is priced at $1.82 that the supplier is willing to supply 9,400 or 9,400 million bushels. Okay, now let's skip the consumer for now. Let's look at what happens when the price increases. So when the price increases to $1.94, then the supplier is going to supply 9,800 million bushels. So when the price goes up, then the supply would go up. So we know that Q, or I'm going to use X here, but we know that X is 9,400 when the price is $1.82, and we know that X is 9,800 when the price is $1.94. So what I'm going to do here now is I'm just going to find the slope of the line that connects these two. So I'll use my slope formula, 1.94 minus 1.82 over 9,800 minus 9,400, and that gave me a slope of 0.003. Now, my equation is going to be in the form of P equals mx plus b. So what I can do, I know the slope, but I don't have the b value. So what I can do is I can plug in a point here, and so I'm going to plug in the point $1.94 and 9,800, and this should be 9,800. The answer is correct though. So anyway, I plug in $1.94, and then here I plug in 9,800 for the x value. And then if you solve this, 0.003 times 9,800 is 2.94. And then if you subtract 2.94 for both sides, you'll get b equals -1. So the b value is actually -1. So now that I know the slope and I know the b, I can say the supply equation is 0.003 minus x minus 1. Now, to do the demand equation, I need to go back to the $1.82 and see what the demand is. So the demand is 9,500. So the demand for $1.82 is 9,500. And what's the demand for $1.94? The demand for $1.94 is 9,300. So I know that when the price is $1.82, demand is 9,500. When price is $1.94, the demand is 9,300. So now solve this just like before. Calculate your slope, $1.94 minus $1.82 divided by 9,300 minus 9,500, and that's going to give me a slope of -0.006. And then use the same formula, P equals mx plus b, and let's go ahead and plug this point in. We'll plug in $1.94 for P and 9,300 for x, and then we'll solve for b. And so when you multiply these two together, you get -5.58 plus b, and that equals $1.94, and then just add 5.58 to both sides to get b equals 7.52. So now we have the slope is -0.006 and the b is 7.52. So that gives me my demand equation. And I'll leave you to go ahead and find the equilibrium point. The equilibrium point occurs at a price of $1.84, and then the quantity is 9466.67, or you might just round that to 9467 for the quantity. Now on the next section, I'll show you the third method that you can use to solve systems of equations without matrices, and that's called the addition or elimination method.